So here we have two graphs that are both position graphs. Forgot to label one of them. Let me fill that in. So these are both X versus Y graphs taken at two different instants in time. And so you could think of these as like snapshots or video that is paused. Like we have a video of a wave and we pause it at 6 seconds and look at what the wave looks like. And we also pause the video at 10 seconds and look at what the wave looks like. So what information can we find from these graphs if they're both X versus Y? I should probably fill in high and low points also. Let's say that's up to 5 and down to -5. So what information can we get from these X versus Y graphs?
I guess the first thing would be wavelength, because time is now constant. So.
Exactly. We can't really tell anything about time yet, but we can definitely measure length of one wave. So for instance, one cycle would be from where to where, for example?
Like for example, like +5 to another +5. Like I guess it's a crest.
Yeah, in terms of the Y values, a high point to the next high point.
Okay.
So this would be one full cycle. And that's convenient because we actually have X values for those. From 4 to 10 is definitely one full cycle. So how far is that?
That would be 6.
Yeah, so we can say the wavelength is exactly 6. And let me fill in the wave equation for future reference. We know the wavelength is 6. We can get that directly from the graph. And also, since it goes up to 5 and down to -5, what does that tell us?
Does that tell us the amplitude?
Yeah, amplitude is just going to be 5 because it's 5 above and 5 below the center line. Also, since it's centered at y = 0, we don't need a plus anything after the sine function. So we know the amplitude, we know the wavelength. Five and 6. And let's say that's measured in meters. I didn't list any units of measurement here, but let's assume all the distances are in meters. And can we find the period or frequency from these graphs? Or what sort of graph should we be looking at if we're looking for period and frequency?
Like y over time?
Yeah, we would need a time versus y graph in order to find period and frequency directly. So we can't directly get period and frequency from this graph. But if we know wavelength, what other information would we need in order to calculate period or frequency? How else are wavelength and period related to each other?
Is it the velocity?
Yeah, if we take a look at the velocity, the speed of the wave, that's going to be equal to wavelength times frequency. Wavelength times frequency, or wavelength times period, same thing. Or sorry, not times, divided by. Wavelength divided by period, that is distance divided by time. Distance for one cycle divided by time for one cycle equals distance over time, so that's speed. In this case, we know the wavelength. If we also had the speed, then we can find the frequency in the period. So let's say that the speed is given. Let's say we happen to know that the speed of this wave is, let's say, 2.5 meters per second. And this would have to be given information. And one reason why we might already know that, what determines the speed of a wave? What determines how fast a wave is able to move?
The medium.
Right. So if this is, let's say, a certain type of wave in a certain type of material, maybe we happen to know the speed of that wave in that material. Maybe we've measured it already, or maybe we can look it up. So let's say we happen to know that the speed of this type of wave in this type of medium is 2.5 meters per second. In that case, we should be able to solve for the speed. If we fill this in, or sorry, we know the speed, we're trying to solve for frequency. So how would you find frequency in this case? How would you isolate frequency in that equation?
Would you divide it by a wavelength?
Yeah, speed over wavelength should work. We know the speed, 2.5 meters per second. Or it'd probably be easier to write that as a fraction, 5/2 divided by the wavelength, which is 6. So 5/2 divided by 6 would be 5/12. So 5/12. And what are the usual units of measurement for frequency? If we've got meters per second and we're dividing by meters, what's left?
Oh, is it 1/seconds?
Right, 1/seconds, also known as hertz. 1 hertz means 1 cycle per second. So we know the frequency. Frequency is 5/12 hertz. And how would you translate to the period? How does that relate to the frequency?
Would you just do the inverse of the frequency?
Right. Period is 1/frequency, because frequency is cycles per second and period is seconds per cycle, amount of time for 1 full cycle. Inverse of 5/12 would be 12/5. Inverse of 1/seconds is seconds. So 12/5, or what, 2 2/5, so 2.4 seconds. So we now know the period. Period is 2.4 seconds. And if we need the frequency is 5/12 hertz. That is 5/12 of a cycle happens every second. And we can now fill in period in the original sine function. Period is 2.4 seconds. Any questions on that so far? So what's left? What do we still not know about the original, the sine function? What do we still need to figure out?
The phase constant.
Yeah, we're missing the phase constant. And what other information is missing here?
Oh, I don't know what it's called, but it's like why not, like added on the outside.
We actually do have why not here, because since this is centered at 0, like it's going up to 5 and down to -5, what's the average of 5 and -5?
Like, wait, 0. I don't know why that took so long.
Which means we can just have a +0 afterwards.
Yeah.
So we don't actually need a why not in this case. But before we find the phase constant, we still need to figure out, should this be plus or minus? And what determines whether we use plus or minus in this wave equation?
Oh, is it the direction it's moving?
Right, so we're going to need to figure out the direction of travel. Once we know the direction of travel, then we can find the phase constant. And the main problem here is that we only have an x graph and another x graph. Typically, if we've got an x graph and a time graph, position and time, we can find a point in common. We can find a single point on the position graph and a single point on the time graph that represent the same coordinates, same position and time. We can't do that here though, because this entire first graph is at time 6 seconds. And 6 seconds doesn't appear on the other graph because the other graph is all time 10 seconds. So there is no point in common. But what we can do instead is identify a single piece of the wave, a single crest or trough, or even a single equilibrium that moves to a new location at the new time. For example, let's say we consider, I would pick probably a location somewhere near the middle. Let's say we're looking at maybe this trough at 7. We know that there's a trough at x equals 7 meters at time 6 seconds. So let's make a note of that. At time, that's going to be difficult to read. At time t equals 6 seconds, a trough passes by the point x equals 7 meters. What we want to do here is find the same trough on the other graph. And of course, it won't be at x equals 7 meters anymore because it moves during that time. Specifically, how much time passes between these two graphs?
4 seconds.
Right. 10 seconds is 4 seconds after 6 seconds. So 4 seconds later, that trough is no longer going to be at 7. It's going to be somewhere else. We don't know if it's gone to the left or to the right, but we can figure that out based on the amount of time. We know 4 seconds pass. Can you figure out how far that trough travels in 4 seconds? What do we know about how fast the wave is traveling?
Maybe we use its speed.
Yeah, we know its speed. Its speed specifically is 2.5 meters per second. We also know the amount of time taken is 4 seconds. We could call that delta t. We want to know delta x, how far it travels. How is speed defined? How is speed related to these other quantities? What is the meaning of speed in physics?
Distance over time.
Right. Distance traveled, delta x, divided by time it takes, delta t. We know delta t, we're trying to find delta x. How would you isolate delta x in this equation?
Oh, would you multiply the difference in time by both sides?
Yeah, multiply both sides by delta t, we get speed times time. So the speed the wave is traveling times how much time it takes, in this case 4 seconds, equals the distance traveled. So if we fill that in, speed is 2.5 meters per second, time is 4 seconds, and what do we get?
That should be 10.
Yeah. So that means the delta x is going to be 10 meters. During these 4 seconds, that point has to travel 10 meters. We don't know if that's 10 meters to the left or 10 meters to the right, though. So we should be checking several points, I think. The problem is if you start at 7 meters and go 10 meters to the left or 10 meters to the right, what locations do you get to?
Sorry, could you repeat that one more time?
If you start at x equals 7 meters, which is the point we chose, if you go 10 meters to the left, what's your new x value?
Oh, -3.
And if you go 10 meters to the right?
17.
And -3 and 17 are off the chart here. They're off the graph. We could draw the graph further in both directions, but that might be kind of inconvenient. So it might work better, instead of looking at 7, Let's try looking at a different location. Maybe let's try, for instance, we know that there happens to be a crest at 4. 10 meters to the left would be off the chart, but what's 10 meters to the right?
14.
Yeah. So if we take a look at x equals 14 on the other graph, what's going on at x equals 14 on the other graph? Is that a crest?
No.
Yeah, it doesn't really look like it. So this the crest at 4 meters is not moving to the right, because if it did, it would get to x equals 14 by 10 seconds. And it doesn't look like there's a crest at x equals 14. So that's not going to work. So we know it's not moving to the right. But let's try moving to the left. Let's say, suppose you are looking at maybe a trough on the far right side, this trough at 13. We know there's a trough at 13 meters at time 6 seconds. 10 meters to the right would be way off the chart, but what's 10 meters to the left?
Three.
Right. So if we check x equals 3 meters on the other graph, what's going on at x equals 3 meters?
It's a trough.
Right. Which suggests that's the same trough. Because we've got a trough at time 6 seconds, if that travels 10 meters, here's a trough at 10 seconds that's exactly 10 meters away. So these two troughs are 4 seconds apart in time and 10 meters apart in space, which is exactly what we should expect based on the speed. And specifically, that point has traveled 10 meters to which direction?
To the left.
Yeah. So we can now, we can now say that point has traveled 10 meters to the left. It looks like this wave is indeed traveling to the left. And if you're not sure about the direction from the graph, you can mark out the 2 points in time we know. We can say that we know that at time 6 seconds, the trough passes x equals 13 meters. And we can also say at time 10 seconds, the same trough passes x equals 3 meters. And a very useful way of sketching this out, again, if you're not sure which direction it's moving, is to make essentially a number line. We know the important locations are 13 and 3. Because we know there's a trough that crosses 13 meters and also crosses 3 meters. Which one does it hit first, though? Which one of these happens earlier? Would you say 6 seconds or 10 seconds is an earlier time?
6 seconds.
Yeah, 6 seconds is earlier. So the first thing it does, the first thing this trough does is pass the 13 meter mark. And then 4 seconds later, it passes the 3 meter mark. So which direction has it moved?
To the left.
Yeah. So if you're not sure which direction it's moving based on the graphs, it often helps to draw out this number line, essentially drawing out just an x-axis, and ask yourself which location does it hit first and which location does it hit later. This is especially useful if you have 2 time graphs instead of 2 position graphs, because on time graphs, it can be difficult to get a read on which direction it's traveling. But as long as you've got what location the trough or crest or whatever passes at what time, then you can draw out your own x-axis and ask yourself which direction is it moving to get from location to location. So we now know for sure this wave is moving to the left. How do we represent that in the equation itself?
Using a plus sign.
Yeah, you want plus. So let's go ahead and fill that in. Plus. And now that we know direction, the only unknown left is the phase constant. So we can now solve for that. Any other questions on finding the direction before we check the phase constant?
For the equation, is that just something we have to know? Like the plus sign goes to the left, the minus goes to the right.
It is a good thing to memorize, but there is actually a reason for it. It's not just arbitrary. The reason ultimately, we want the time term and the position term to balance each other out. As time passes, the time term is increasing. So the time term is increasing as time passes. Also, as time passes, this wave is moving to the left. So if you're following one crest or one trough, what's happening to the x coordinate of that trough as it moves to the left?
It's decreasing.
Right. So that means this whole position term is decreasing. In order for an increase and a decrease to balance out, should we be adding or subtracting?
Oh, should we subtract it?
If we subtract, then this one's getting bigger and the thing we're subtracting is getting smaller. So the result's going to get bigger and bigger and bigger.
Oh, I'm adding it then.
Right. If we add, then one thing gets bigger and the other gets smaller. So the total stays balanced.
Oh, okay.
On the other hand, if it was moving to the right, then x would be also increasing as time passes. So you'd have an increase and an increase. If you added those, it would just get bigger and bigger. So we would want to subtract so that the increase minus the increase balances each other out. So ultimately, that's why we want the changes to balance each other out if we're keeping track of one crest or one trough as it moves.
So it's like you kind of want the signs to cancel out, I guess.
Essentially, yeah. If it's moving in the positive x direction, you want a minus to balance that out. If it's moving in the negative x direction, you want a plus to balance that out. Any other questions on direction so far? Then let's take a look at the phase constant, see if we can solve for phi. To solve for phi, how would we get information from these graphs in order to do that?
You could pick one graph. So like, for example, time is 6. And then you can also choose a point on that graph for x and y, and then solve for that constant.
Yeah. And typically we want to pick a crest or trough to avoid ambiguity. Because if you pick like an equilibrium point, equilibrium shows up twice in each cycle, so that's ambiguous. But if we choose a crest or a trough, like what would be a coordinates that are definitely a crest or definitely a trough?
Like x equals 4, and then y equals 5.
Sure, let's go ahead and use that. We know that we have a crest at x equals 7 meters and t, what's the t coordinate for that point? What time is that happening at?
6 seconds.
Yeah, because this whole graph is at 6 seconds. So we know there's a crest when x equals 7 and t equals 6. And also y is 5. But we don't actually need to know the y value. Because instead of looking at the entire equation, and this is one way to do it, you could fill in 7 for x, 6 for t, and 5 for y, and then solve for phi. But we don't actually need the entire equation. We could look at just what's inside the sine function. The idea of the total phase. Use the total phase, just all this stuff inside the sine function. If we're at a crest, what does the total phase have to equal?
Like pi over 2?
Yeah, because if you take the sine of pi over 2, you're going to get 1. which is the highest the sine function can get. Or alternatively, at a trough, what would you use for the total phase? What input would make the sine function as low as it can get?
3 pi over 2.
Right, through sine of 3 pi over 2 would be as low as it can get. Alternatively, you could use negative pi over 2 to get a trough. So if you're at a crest, set the total phase, the stuff inside the sine function, equal to pi over 2. If you're at a trough, set the total phase equal to 3 pi over 2 or negative pi over 2. Either way works. And we know values of time. Time is 6 seconds, and position is 7 meters. We can also cancel out the units. Seconds over seconds cancel out, and meters over meters cancel out. So we now have an equation with just phi in it as the only unknown left. So let's try simplifying this a bit. 2.4, let's go ahead and write that as a fraction again. That was 12/5. So dividing by 12/5 is the same as multiplying by 5/12. 2 and 6 multiplied to 12 times pi times 5/12. 2 and 6 reduced to 1 over 3, so we get 7 pi over 3 plus the phase constant equals pi over 2. And what else can we do here to simplify things?
You could divide both sides by pi and then also multiply that 2 over.
First of all, though, every numerical term has a pi in it, but phi doesn't. So I would go ahead and leave the pi there.
Okay.
But we can reduce further. For instance, 12 pi times 5 over 12, what does that reduce to?
Just 5 pi?
Yeah. So we got 5 pi plus 7/3 pi plus phase constant equals pi over 2. Also, 5 pi, that's pretty big. If we split that up into 4 pi plus another pi, what do you know about 4 pi? How many cycles is that?
Oh, is it 2 cycles?
Yeah, that's exactly 2 cycles, a whole number of cycles. And any whole number of cycles can be ignored. We can just leave off that 4 pi. Because if you're pointing in some angular direction and you go one full cycle and another full cycle, you're still pointing in the same direction. An extra plus 2 pi or an extra plus 4 pi or plus 6 pi or minus 2 pi, plus or minus any whole number of 2 pi can be ignored. So I would just treat this as pi plus another 7 pi over 3. In fact, we could probably go even further because 7 pi over 3, that's more than a full cycle. 7/3 is, what would that be as a mixed number?
Uh, 2 1/3?
Right. So this could be written as 2 pi plus an extra 1/3 of pi. And 2 pi is also a full cycle, so we can ignore that as well. So 7 pi over 3 is the same as 2 pi plus an extra pi over 3. The 2 pi can be ignored. So we can reduce this to just pi plus 1/3 pi. And that'll just be 3/3 pi plus 1/3 pi. So 4 pi over 3 plus phi equals pi over 2. And we'll probably want a common denominator here. What's the smallest denominator that's a multiple of 3 and 2?
6.
Yeah, so let's turn these into sixths. 4 pi over 3, we can just multiply numerator and denominator by 2. So 8 pi over 6 plus phase constant equals, and then pi over 2, let's multiply that by 3 over 3. So 3 pi over 6. Now everything is at least in the same denominator. And now what's the only thing left to do to solve for phi?
Just move the other numbers to one side and then just solve.
Yeah. So if we just subtract 8 pi over 6 from both sides, we get 3 pi over 6 minus 8 pi over 6. And that'll be negative 5 pi over 6. And one other thing we want to do there, a negative phase constant, we could just leave that as it is. This is a viable answer. But it's usually easier to work with if you have a small positive number for the phase constant, somewhere between 0 and 2 pi, the first full revolution. So what could we do to this? What could we add to the phase constant that doesn't actually change anything?
2 pi.
Yeah. So let's take our negative 5 pi over 6 and add 2 pi. That'll make it positive. 2 pi in sixths is going to be 12 pi over 6. So we're just adding one full cycle. No real change to the meaning, just changing the way we're writing it as a number. Negative 5 plus 12 would be 7, so 7 pi over 6. So that's what I would use as the phase constant here. So back to the original equation, 7 pi over 6 is our phase constant. And so that should work as our wave equation. We got our amplitude, period. Yeah, go ahead.
For the symbol for total phase, is it just phi?
Usually we use a capital phi for total phase.
Okay.
So, and those can be kind of difficult to tell apart depending on the font.
Okay.
So that'll look like, yeah, some fonts make it very difficult to tell capital versus lowercase. When drawing it by hand, I would write it as with serifs. So like this. If you put in serifs like this, the bars at the top and the bottom, that makes it a lot more clear that it is a capital phi.
Okay.
So capital phi is the total phase, everything inside the sine function. Lowercase phi without the serifs, and maybe a little smaller, is just the phase constant, the plus a number outside of the t and x terms.
Oh, does the phase constant, does that have, like, what does that mean? Or is it just like a term that we add?
It's ultimately to do with the initial conditions, like in terms of what's going on at the source. Because if that wasn't there, like let's say that phase constant wasn't there, if we didn't have a phase constant at all. In that case, if you were to fill in 0 for t and 0 for x, what would you get?
You would just get 0.
Yeah, without a phase constant, y equals 0 when x equals 0 and t equals 0. Which means without a phase constant, every wave would be passing through the origin at time 0. That is, passing through equilibrium. And that's not true. A wave could be starting at any height at time 0. Maybe you're, for instance, maybe you're holding a rope and you're shaking it. Let's say you're at the high point at the time we're calling 0. That wouldn't work if there was no phase constant. No phase constant would mean you'd have to be passing through equilibrium at time 0. And that doesn't make sense physically. You could be anywhere in the cycle at time 0. So phase constant really has to do with making the equation make sense based on where the source is at time 0. And also to some extent, it depends on the coordinate system, like what time we start the stopwatch. But we need the phase constant to make sure that the wave doesn't have to be passing through the origin at the time we're calling 0.
Okay. And I guess like the other term, the plus y naught, that one was only if it's the amplitude doesn't like average out to 0.
The plus something outside of the sine function?
Yeah.
Yeah, if you had a wave that wasn't centered at y equals 0. Like for instance, let's say your wave was, maybe it was the same shape, but it was higher up. Like instead of oscillating between 5 and -5, let's say it was oscillating between like 8 and -2. In that case, you could accomplish that since we're just taking the whole graph and shifting it up 3 spaces. You could accomplish that with just an extra +3 outside the sine function. And that behaves exactly like a plus a constant for any function. Like if you just take a quadratic, y equals x squared. If you change it to y equals x squared plus 5, you're just shifting the parabola up 5 spaces. So this behaves exactly the same way. Plus a constant outside the function just shifts the whole graph up or down that many spaces.
So I'm not sure if this is right. So would it be right to say that like the phase constant shifts it like on the x-axis, I guess?
Yeah, well, the x-axis or the t-axis.
Mm-hmm.
Because this, if it's a y versus x graph versus a y versus t graph. So the phase constant, since it's something being added inside the function, that shifts it in the direction of the independent variable. But since this is a function of 2 variables, the phase constant could be interpreted as shifting in the x direction or in the t direction or both at the same time. But it's a modifier on both position and time.
Okay, that makes sense.
And it's also going to be, it can be treated as an angular measure. It's measured in radians because it's being added to these other terms that are also measured in radians. In fact, everything inside the sine function in total has to be a radian measure because you're taking the sine of an angle.
I have one more question. So like instead of position, there were time. Would we be what would we be able to like take from that? I guess.
Like if you had 2 time graphs?
Yeah.
You can actually do almost exactly the same process. If you had 2 time graphs, it's just going to reverse a few things. 2 time graphs means that you would know the period and frequency, but you wouldn't know the wavelength. But again, if you know the speed, you can solve for the wavelength. And likewise, if it's 2 time graphs, then instead of having a time for the first graph and a time for the second graph, you'd have a position for the first graph and a position for the second graph. So you could figure out the difference in position. Like let's say you had one of the graphs was x equals 5 meters and the other one was x equals 12 meters. If it's 5 and 12, how much distance is that?
Would it be 6?
From 5 to 12?
7.
Yeah. So if you have one time graph that's at x equals 5 and another that's at x equals 12, that would be 7 meters apart from each other. So you could interpret that, once again, if you think of this as creating an x graph. Let's say you have measurements at x equals 5 and x equals 12. You could interpret that as you've got like 2 measuring stations. You've got somebody keeping watch on the wave at the 5 meter mark, somebody keeping watch on the wave at the 12 meter mark, and watching as those 2 points bob up and down. And so the graphs would be showing just the 5 meter mark bobbing up and down as time passes, and just the 12 meter mark bobbing up and down as time passes. So in that case, you would know the delta x already, but you wouldn't know the delta t. But again, if you know speed and you know one of the deltas, you can find the other one. So in that context, you would know delta x is 7 meters because the 2 measuring stations are 7 meters apart. And if you know the speed, you can solve for how much time it takes for the wave to travel from one measuring station to the other. And then you can use a very similar procedure. Choose one time, probably near the center of the graph, look that far into the past and that far into the future, and see if you can find another spot of the same type, same crest or same trough on the other graph. So it's essentially the same procedure. We're just reversing the use of position and the use of time. And then once you can figure out which one of these points the crest hits earlier, like let's say you find that the crest hits the 5 meter mark earlier and then hits the 12 meter mark later, that would mean it's moving to the right. Any other questions on that?
Yeah, could we walk through one where it's position or y versus x and then a y versus t, like just that thought process?
If you've got both of them?
Yeah, I do have like the f and t pulled up. Should I
Yeah,
like
let
screen?
me actually pull up another example that I think will
Okay.
go there. One moment. Here's another example with an x versus y graph and separately an x versus t graph. Can you see this one all right?
Yeah.
So in this case, usually the procedure would be to find what we call a point in common, like the same point on both graphs. And in this case, we can, because the top graph is all x values, but only which t value?
At time equals 2.
Right. So since this whole graph is at time 2, we're going to look for time 2 on the other graph. And it looks like time 2 is here, almost a crest, but not quite. Looks like it's at maybe y equals 50. So that's time 2, but also what x value?
X equals 10.
Right, because the whole graph is at x equals 10. So we want to take a look for x equals 10 on the other graph. X equals 10 is right here. Also almost, but not quite at a crest. So if we label the coordinates of these points, this point has coordinates x equals 10, t equals 2, because the whole graph is at t equals 2. Y equals, I'm just estimating here, that looks like about 55. And then this one is x equals 10, because the whole graph is at 10. T equals 2, because it's that point on the graph. And also y is about 55. So these 2 points represent the same information. They represent that at time 2, the location we're calling 10 is 55 high as the y value. So we've got a point in common. We can't do that on 2 x graphs or 2 t graphs, but we can do that if we have one of each. Any questions on that so far?
This is just like a general question. So like when we're looking at these two graphs, they're the same graph, I guess. But
they're 2 different ways of looking at the same equation. They both represent the same wave. We're just looking at it from 2 different perspectives. The x graph could be thought of as the shape of the wave frozen in time. Like as the wave travels, if you've got a video of it and you hit the pause button, the x graph shows what the wave looks like at that instant in time, frozen in time. Whereas the t graph is showing all time, but only one position. So like if you've got this wave that's moving around and you mark a location on the wave and watch just that location as it bobs up and down, the time graph is essentially a history of that one location as it moves up and down as time passes. So both of the graphs are describing the same phenomenon, the same wave. They're just looking at it from 2 different perspectives. The snapshot versus the history. And if we want to know what happens next, because we know what's happening at 2 seconds, we know the wave is at y equals 55. If we want to know what happens next a little bit into the future, which graph should we look at?
Y versus t.
Yeah, the time graph gives us information about the future, what happens a little bit later. So based on this graph, is this point at 55 on its way up or 55 on its way down?
On its way down.
Down? As time passes, yeah, if we go a little bit into the future, because remember on this graph, left means into the past, right means into the future. So a little bit into the future, we're now at a slightly higher y value. So we can interpret this, that specifically this positive slope, as the fact that this point is on its way up. Going back to the x graph, now that we know this is 55 on its way up, we can ask ourselves, if the graph itself moves left versus right, would that cause the point to move up? So looking at the graph itself, would this graph moving to the left or to the right cause the point to move up?
To the right.
If the graph moves to the right, that's going to allow this point to sink.
Okay.
Because remember, the point isn't moving left or right. The point is just bobbing up and down. The graph itself can move to the left or to the right.
Okay.
And if the graph moves to the left, that's a crest moving towards this point. So that means this point is able to shift up as the crest approaches it. So we should interpret this as the graph is moving to the left.
That makes a lot more sense. Thank you.
You're welcome.
Yeah.
And I often think of it as, should I expect the nearest crest or the nearest trough to be moving towards it? If we want this point to move up, we want the nearest crest, which is about 11, to move towards it. So that means the crest has to move to the left. Any other questions?
That's it for me. Thank you so much for staying over time.
Yeah, you're welcome. So give this a try. There's some similar graphs on the FNT. And also if you go to math.ncheese.org/P7C, I've got a practice worksheet with some similar problems if you want some more practice. So try that out and I will see you next time.